So tired. Okay. All right, I'm just recording this to send out to people, just something that's most likely going to come up on the chemistry exam, and that is structure and bonding. So, it's going to get into this. You need to be able to spot which of these compounds are ionic compounds, which are covalent, or which are metallic. They're not all compounds, obviously. We've got Cu there and Na, which are elements from the periodic table. But you need to be able to spot what type of compounds these are. So, just going to go through how you do that. Okay, so look at the first one is ammonia, and it contains nitrogen and hydrogen. They're both non-metals, so that makes it covalent. The next one is sodium chloride. Sodium's found on the left side of the periodic table. It's a metal. Chlorine is a non-metal, so we have metal and non-metal, and that's ionic. Carbon monoxide is two non-metals, so that's covalent. Hydrogen chloride, two non-metals, that's covalent. Calcium chloride, calcium's in group 2, it's a metal. Chlorine's a non-metal, so that's ionic. So you can see you're going through and you should be able to spot if it's a metal and non-metal, it's ionic. If it's two non-metals, it's covalent. We've got these last two here, I and J. We've got Cu, which stands for copper, and Na, which stands for sodium. They're both metals, so they're metallic substances. They have metallic bonding. So here's how to spot the ionic. You go, right, sodium's a metal, chlorine's a non-metal. That makes it ionic. And if we look at the periodic table here, we can split the periodic table into metals on the left over here, and we have non-metals on the right. So when you have a combination of elements in your compound from the left and the right, it's ionic. If it's just non-metals here circled in green, it's covalent. And if it's just metals, it has metallic bonding. Okay. So all of these ones I've circled here contain a metal from the left of the periodic table and non-metals from the right of the periodic table, and that makes them ionic. These are metallic, and these guys here are covalent. Right. Just messing around with the old screen. Zip that up there. Okay, you need to know these three definitions. Now, a lot of people think the definition of a covalent bond is just a shared pair of electrons. That's not right anymore. Back in the past, 5 years ago, you would have got the marks for saying that a covalent bond is a shared pair of electrons. You don't get the marks for that anymore. So there's three definitions for the three types of bonding found in chemistry. So the three types of bonding you find in chemistry, you have ionic bonding, which is the electrostatic forces of attraction, I've underlined here in black, found between oppositely charged ions. So for 2 marks, the forces of attraction, or even better if you can remember, it's electrostatic forces of attraction found between oppositely charged ions. For covalent bonding, the answer starts the same. It's the electrostatic forces of attraction, but this time it's between shared pairs of electrons and nuclei. And for the final one, which is metallic bonding, the definition is the electrostatic forces of attraction between delocalized electrons and positive metal ions. So now we've got these modern definitions. You have to say both of these. Start with the electrostatic forces of attraction. That's the same for all. And then you finish with the correct second part of the definition. All right. So when dealing with structure and bonding questions, and about 10 marks of your exam on Monday is going to be structure and bonding in the first chemistry paper. So here we've got one. Explain why sodium oxide has a high melting point. So why does sodium oxide have a high melting point? The first thing you've got to do is look at sodium oxide and say, right, what are they? Get my periodic table out, go to your data sheet. Sodium is a metal, it's on the left. Oxygen is a non-metal, it's on the right. We have an ionic compound. So we now know the name of the bonds. They're ionic bonds, which means I can write the definition. It has strong electrostatic forces of attraction between oppositely charged ions. That's an ionic bond. if I can't remember that, I can just write it has ionic bonds, and I might grab a mark. We also have to know about something called structure. Structure is different than bonding. Bonding comes in 3 flavors: covalent, ionic, metallic. Structure comes in 2 flavors: giant or simple. So if you get in a question, you should have your highlighter and you should be highlighting the questions. If you see the words structure and bonding, explain this, talk about the structure and bonding, you need to say the words either giant or simple, because the structure of every chemical or every material or every substance is either giant or simple in chemistry. So if you're asked to talk about structure, you need to say giant or simple. And there's a way you can work out what it is. And then if you're asked also to comment on the bonding, you need to say ionic, metallic or covalent. So here's how to work out the structure. How do you know whether something is giant or simple? Well, every single ionic compound, metal and non-metal, that are joined together has a giant structure. There are no ionic compounds with a simple structure. So anytime you have sodium chloride, sodium oxide, you have a metal and non-metal, magnesium oxide, that is ionic and so has a giant structure. Anything that's a metal, copper, silver, gold, magnesium, lithium, sodium, they have a metallic structure and that's also giant. So if you're given a ionic compound or a metal, it's giant. So here's the clue: look for the name of a metal, then it's a giant structure. You can then work out the bonding. If it's non-metal and metal, it's ionic bonding and a giant structure. If it's just the metal on its own, it's metallic bonding and a giant structure. Okay, now covalent, some are giant and some are simple, so that's more complicated. We'll get into that in a little bit. Essentially, any covalent substance that's a gas or a liquid at room temperature is 100% simple. Carbon dioxide, water, nitrogen in the air, oxygen in the air, methane, the natural gas we burn, ethane, any of these substances are simple because they're gas or liquid at room temperature. Water, as I mentioned, is a liquid in your room right now. That means that water is a simple structured substance. Okay? Anything that has a low melting or boiling point and is a solid, like plastic, if I take a match to my plastic cup here or my biro, it's going to melt pretty easily. This means this plastic is a simple substance. It has a simple structure. Iodine is a substance that when you heat it, it's a solid, it's a black or dark grey crystal. When you heat it, it vaporizes straight away, skips the liquid phase, it sublimes by sublimation. And that's because it has a simple structure. So there's a lot of clues to tell whether something's giant or simple. Let's get a bit further into it. So going back to this question, explain why sodium oxide has a high melting point. I can mention that it's got ionic bonding because I spotted that from metal and non-metal. And if I can remember, I'll give this definition: strong electrostatic forces of attraction between oppositely charged ions. I then want to say it's got a giant structure, which I know because of the high melting point and because it's ionic. All ionic substances have a giant structure. And when you say the words giant structure, there's a whole bunch of other marks you can get. So if you say the words giant structure, you need to follow it up with lots of strong bonds, lots of energy needed to break. So there's 3 marks or 3 key points you can get for just saying the structure. So going back to here, I can say sodium oxide has a high melting point because it has strong electrostatic forces of attraction between oppositely charged ions. It has a giant structure. It needs lots of energy to break the many bonds in the giant structure. To be honest, that's a 4 or 5 mark answer, and it's only a 3 mark question, so you're going to get all the marks there. Right. Let's look at a different style of question. 3 marks as well. Explain why ammonia has a low boiling point. Notice I've used a highlighter. That's an important thing that you should be doing in exams, is using a highlighter. So why does ammonia have a low boiling point? Look what it said in the question. Talk about the structure. Talk about the bonding. I'm going to get 2 out of the 3 marks for naming the structure and the bonding. Is it a giant structure or a simple structure? It says it's got a low boiling point. It's a gas, ammonia. If you know that, you're onto it already. The fact that it says low boiling point, anything with a low boiling point, anything that's a liquid or a gas, is a simple structure. Giant or simple? It's simple. Now its bonding, is it ionic, covalent or metallic? Well, it's made of nitrogen and hydrogen. Are they metals or non-metals? They're non-metals, so it's covalent bonding. So it has a simple structure with strong covalent bonds. There are no such things as weak bonds in chemistry. And the reason why it's a gas is not because it has weak covalent bonds. Never put the word weak with bond in chemistry. So it's actually a gas because of something else. You're not trying to break the bonds when you turn ammonia into a gas. You're trying to separate forces. So we'll get into that. So I'm going to score 2 marks if I say, yeah, it's got covalent bonding and a simple structure. Whenever we say the word simple structure or use the word simple in chemistry, we need to follow up with these answers. Weak intermolecular forces, only a little energy needed to break them. So we have a giant structure, lots of strong bonds, lots of energy to break. And then we have simple structures, weak intermolecular forces, only a little energy to break. I steer away from talking about bonds with simple because the covalent bonds in ammonia are actually stronger than my ionic bonds in sodium oxide. They actually take more energy to break, but I'm not looking to break those bonds when I want to turn ammonia into a gas. I just want to break the forces in simple structures, and they have weak forces. Okay, let's go through some more examples. There's our answers. So why was ammonia a gas at room temperature, or why does it have a low boiling point? It's got a simple molecular structure, or small molecules. Weak intermolecular forces, only a little energy is needed to overcome those forces. Right, let's go through some other examples. Chlorine reacts with hydrogen to form hydrogen chloride. Highlighted that. Explain why hydrogen chloride is a gas. This is a structure and bonding question. Oh, it even says answer in terms of structure and bonding. So I'm going to get a mark for naming the structure, a mark for naming the bonding. It tells us it's a gas at room temperature. Does that sound like a giant structure or a simple structure? If you're a gas, a liquid, or you have a low boiling point or melting point, if you're soft, if you're a solid, you are simple. So we have a simple structure. What's the bonding? Hydrogen and chlorine are non-metals. It's covalent bonding. In fact, simple structures only have covalent bonding. So the moment I decide something is simple, I also know it has covalent bonds. Don't forget, covalent bonds are very strong. Don't mention that they're weak. Don't say weak bonds. You're going wrong if you start talking about weak bonds. So, saying it's a gas is the same question as saying why does it have a low boiling point. So it's simple, weak intermolecular forces, not a lot of energy needed to break them. And here's the exact mark scheme from the exam board. Hydrogen chloride is made of small molecules. It's better to say simple structure than small molecules. Hydrogen chloride has weak intermolecular forces. We said that. Requires little energy to break. We said that. Did I need to mention that it has covalent bonds? No, it's not on the mark scheme, but they did ask me to mention the bonding. And why did they say that? They count weak intermolecular forces as you discussing the bonding. Right, got another one. Describe 4 marks. Describe the structure and bonding in sodium chloride. This one's a bit tougher. It hasn't told me if it's got a high melting point. If they say high melting point, I know it's giant. But if they say low melting point, I know it's simple. But they ain't told me anything about the melting boiling point or whether it's gas or solid. What I can do here is then go to my, is it ionic? Is it covalent? Is it metallic? Well, sodium's a metal, chlorine's a non-metal. Metal, non-metal, it's ionic. Every single ionic has a giant structure. So we know it's a metal and a non-metal. That means it has ionic bonding. Anything with ionic bonding has a giant structure. So ionic bonding means it has a giant structure, lots of strong bonds, lots of energy needed to break. Woo woo! We've just smashed 4 marks. Okay, so there's some clues here. Once you're onto its giant, follow up with the strong bonds, follow up with lots of energy needed to break. And that's what you need to do. You're pretty much guaranteed to get questions on this in your chemistry exam. It's a fundamental core piece of knowledge that you need in chemistry, and people who are taking GCSE chemistry potentially could go forward to A level. They need to test you on this. Why does iodine have a low melting point? What's the key point? Oops, zing back. I thought I'd highlighted this. Why does iodine have a low melting point? So the key point here is low melting point. As soon as I see low melting point, I know it's simple structure. What's the bonding? Well, I don't even need to talk about the bonding. I say simple structure, follow up with the two key, weak intermolecular forces, not a lot of energy needed to break them. Look here, simple, I've highlighted them in green. Weak intermolecular forces, not a lot of energy needed to overcome them. And that's all you've got to do. Every time something's a gas or a liquid, they ask you about its structure or bonding. It's simple structure. Weak intermolecular forces, not a lot of energy needed to break. And that follows on from the word simple. Let's look at another one. Explain why diamond has a high melting point. Right, now, they even say shows part of the structure and bonding in diamond. They love to talk about structure and bonding. Okay, this question is about structure and bonding. I mean, it's mainly about the structure, but diamond is made of carbon atoms. I've got a question mark there, and carbon atoms are non-metals, so it's covalent bonding. Now, it's very, very strong covalent bonding, and if I want, I can give the definition of a covalent bond, which is the strong electrostatic forces of attraction between positive nuclei and shared pairs of electrons. That's great if I can give that. But I can also just, if it's too much to remember, just go, right, it's got a high melting point, it's giant, lots of strong bonds, lots of energy needed to break. So carbon is covalent, yeah. So covalent, giant, lots of strong bonds, lots of energy needed to break. Let's zing. Come down to just underneath this picture of the kettle and the camping stove. It says, explain why copper, like many other metals, has a high melting point. Why does copper have a high melting point? You see the high melting point again. What structure is it? It then says, describe the structure and the bonding of a metal. What structure is linked to high melting points, hardness, high boiling points, solids? What is this linked with? Giant or simple? Giant structure. As soon as we write giant structure, what were the two other points we need to make? Lots of strong bonds, lots of energy needed to break. And so I'm going to come out, if I just write giant structure, lots of strong bonds, lots of energy needed to break, I'm going to come out of this answer probably with 3 marks, but definitely 2 marks. And I haven't commented on the bonding. The bonding is metallic. How do I know it's metallic? It's made of copper. There's no non-metal there. It's not ionic. It's not covalent because copper's a metal. So it's metallic bonding. I could put the definition of metallic bonding here and work that into my answer. So the definition of metallic bonding is the strong electrostatic forces of attraction. If you can't remember that, just say forces of attraction between positive ions and delocalized electrons. You're allowed to say free electrons. So you can even shorten this down to metallic bonding is the force of attraction between positive ions and free electrons. Okay. It's not perfect, but it will do. And then what are they strong or weak? All bonds are strong. So metallic bonds are strong. So I can say giant structure, lots of strong metallic bonds, lots of energy needed to break. But it's better to give that definition as well. So here we go. It's giant because of the high melting point. It's metallic because it's a metal. So giant, metallic structure, 1 mark. Lots of strong metallic bonds. Even better if I can say I've drawn an arrow. Strong attraction between free electrons and positive metal ions. Need lots of energy to break. And that's going to get me all the marks I need. Look, here's the correct. Here is the mark scheme from the exam board. Giant structure, 1 mark. Made, and then they've given the definition for the second mark. Positive ions and free electrons. Okay, so strong bonds, lots of energy needed to break. Do you see I could have got 3 out of 4 here by just saying giant structure, hitting them with the strong bonds, lots of energy needed to break. 3 out of 4. That's a level 9 on that question. Structure and bonding, people find it really hard, but it's not that hard. Right. Pretty much you are guaranteed on Monday in the exam, your chemistry exam, to be asked about why something conducts electricity or why something doesn't conduct electricity. And they're worth 2 marks. Why does something conduct electricity? All things in chemistry that conduct electricity have to have one of 2 particles in them? Free electrons or free moving ions or free ions? You can say delocalized electrons, it's a better term, but you're allowed to say free electrons. And free ions. Now, there's no substances that really have both. You have one or the other if you conduct electricity. If you don't conduct electricity, guess what you don't have? You don't have free electrons. You don't have free ions. Now, if you have free electrons or free ions, and that's the 50-50 part if they ask you why does something conduct electricity, you say it's got free ions or free electrons. The second mark is the same for all of them. So charge can be carried through the structure, and that's the second mark. So why does iodine not conduct electricity? Well, lots of things don't conduct electricity. My baseball cap doesn't conduct electricity. Why? Okay, my baseball cap doesn't conduct electricity because it's got no free ions and no free electrons, and so it can't carry charge through the structure, or charge can't be carried through the structure, and that's my answer. So iodine has no delocalized free mobile electrons or ions, you didn't have to say both, so cannot carry charge. Boom. Let's look at this question. I'm not interested in the first part. Why are carbon nanotubes used as lubricants? Lubricants is lubricants is because layers can slide. So if layers can slide, then something's good as a lubricant. Graphite, nanotubes, lots of things. Anything that's a good lubricant has layers which can slide. I'm interested in the second part of this question. It says explain why graphite can conduct electricity. Now, graphite is found in your pencil, and why can that conduct electricity? Well, it has to have free ions or free electrons that carry charge. You're only going to get 1 mark if you get the first bit wrong. Graphite is a solid pencil lead. It has free electrons. Any solids that conduct electricity don't have free moving ions. So it has free electrons or delocalized electrons that carry charge, and that's the answer. So you see here, delocalized electrons except free electrons. Not as good an answer, but it'll get you the marks. So electrons can move through the graphite except so they can carry charge. I always just go with carry charge. Right. This question says describe the structure of a metal. The structure of a metal is positive ions and free electrons. So it's a lattice giant structure. Remember, metals and ionic compounds are all giant. So metals have a giant structure. They have free electrons and positive ions. Free electrons surrounding positive ions, or a sea of electrons, as some people like to say. So regular lattice, giant structure. Lattice and giant structure are the same thing. You can use them interchangeably. Some people say macromolecule. Positive ions and free electrons. Right, let's bus on. Right. Describe the structure of silicon dioxide and explain why it's suitable for making welding blankets. People say, oh my God. Right. Welding. Welding involves a lot of heat, and it tells us up the top here, some welding blankets are made from silicon dioxide, which does not melt when hit by sparks. If it doesn't melt, it's got a high melting point. What's the structure? If you've got a high melting point, you must be giant structure. Lots of strong bonds, lots of energy needed to break. And that's why silicon dioxide is great. It's used inside the furnace to line the walls of ovens. It's basically sand. When you look at sand on the beach, that's silicon dioxide, and it doesn't melt. Okay, under incredible heat, it won't melt. So yeah, it's giant covalent. Actually, we can tell it's covalent because it's made of oxygen and silicon atoms. So they're both non-metals, and so it's a giant covalent, not a simple covalent structure, a giant one. And the clue is high melting point. The moment I see that, it's giant. So marks are for saying it is a giant structure made from covalent bonds, strong bonds, lots of energy needed to break the bonds, and they're all the marks. Describe the structure and bonding in metals. Again, we just had this one. What type of electrons do they have? Free electrons, positive ions, and it's a giant structure or a lattice structure or a regular structure. Explain why, and we're interested in the second part here, explain why metals such as nickel and platinum are good conductors of electricity. All metals can conduct electricity. Why are nickel and platinum good? Same answer for all metals. What type of electrons does metal have? They have delocalized or free electrons. What can they do to enable electricity to go through them? They carry the charge through the structure. So, 1 mark from saying they have a lattice arrangement, atoms or ions. I just go for the last 2 marks. Delocalized electrons, free to move, carry the charge through the structure. Graphite is a type of carbon. Why does graphite conduct electricity? Delocalized electrons carry the charge through the structure, guys. Hello. Here we go. Graphite has delocalized electrons, carry electrical charge through the structure. So it's the same answer every time. Why does this conduct electricity? If the substance is solid and it conducts electricity, it must have delocalized electrons. So graphite and metals have delocalized electrons. There are some things that conduct electricity without delocalized electrons. These are ionic compounds, but they have to be melted or dissolved first so the ions can move. They have no free electrons, but they can have free ions when melted or dissolved, and that's for ionic compounds, metals and non-metals. Things like salt that you put on your food, sodium chloride, if you dissolve it in water, I've got a video where I try to conduct electricity through solid salt and it won't conduct electricity, the light bulb doesn't come on, and then I do it through salt in water and the light bulb does come on, and that's because the ions are free to move and carry the charge. Here's another question which I haven't covered today, but I'm just going to whip through these questions and then finish up in like 5 minutes. So steel is an alloy of iron and carbon. Explain why steel is harder. You need to know why alloys are harder. Alloys have different sized elements. And metals, pure metals, like any pure metal, iron, gold, anything that's pure, is arranged in layers, and the layers can slide. That makes them malleable and ductile and all of this because the layers can slide. Alloys have different sized elements put into them. They're a mixture, so we often mix things. With steel, we take iron, it's like 99.8% iron, and then we just put 0.02% carbon atoms in there. The carbon atoms get in the way of the iron layers, they disrupt the layers and stop them sliding. So really the 3 marks here is to say different sized elements. So elements of different sizes. It's not just made of one element with one size. So the different sized elements disrupt the layers or interrupt the layers and prevent the layers sliding. And that's why steel is harder. Ooh, got a little diagram here. I didn't know I did this. So we've got the pure metal there. It's like 6 circles all drawn. They're all the same size. The alloy you can see here is not all the same size, and so the layers don't slide. So the carbon atoms have different sizes, so elements have different sizes, distort the layers, disrupt the layers can't slide. You might get an alloy question that comes up every now and again, so already seen that question. That was on diamonds. I'll skip through that. I'm down the bottom now. Let's go up here. Okay, this is a good question. This could come up in the structure and bonding part of the paper, or it could come up under electrolysis. So this shows sodium chloride. Is sodium chloride covalent, ionic, or metallic? Or sodium's a metal, chlorine's a non-metal? It's ionic. Explain the conditions needed for the sodium chloride to conduct electricity. Right. When ionic substances are solid, they can't conduct electricity because the particles are locked in a lattice. Okay, so they don't conduct electricity when they're like that. So the conditions we need to melt them or dissolve them in water. And there's 2 different things. Melting requires tons of energy and tons of heat and it's very expensive. Dissolving something in water is a lot easier. So if I want to melt salt, it's going to cost me a lot of money. If I want to dissolve salt, just stir it in water and make it dissolve. If I do both of those, if I either melt the salt in a frying pan, or if I dissolve it in water, it will now conduct electricity. And the reason is ions can move and carry charge. Notice carry charge is always there. So I needed to melt them. I need to melt the sodium chloride or dissolve it into a solution. That will give it free ions that can carry charge. And here's the answers. Dissolve the water or melt. Molten means melted. So ions are free moving. We didn't even have to say carry charge on this one. I think you need to add that, and just in case, because exam board to exam board, or like exam to exam, that will be on the mark scheme. Explain why graphite is softer than diamond. Okay, this is something you just need to know. They're both giant covalent structures. They're both made of carbon, so they have strong covalent bonds. The bond between the carbon atoms, they're identical bond strength. So the bond, almost identical. The bonds in graphite are almost as strong as the bonds in diamond. It's the same covalent bond between two carbon atoms. Graphite is slightly soft. Well, graphite's a lot softer. You can write with a pencil, and the graphite rubs off on the paper. That's why you can draw with a pencil. You can't draw with a diamond. It's to do with the amount of bonds. Diamond, each carbon atom has 4 bonds, whereas with graphite, each carbon atom only has 3 bonds. So that's what we're going to get marks for saying that. Diamond, each carbon atom is bonded to 4 others. Graphite, each carbon atom is bonded to 3 others. They're both giant covalent structures with lots of strong bonds, need lots of energy to break, but that's not going to get me the marks in this question. This question's not saying why do they have a high melting point. Both of them have a high melting point. If it was asking me about that, it would be giant covalent, lots of strong bonds, lots of energy to break. This is saying, why is graphite soft? Graphite's soft. If you look, it's arranged like a metal. It's arranged in layers. Now the layers don't have a bond in between them. There's no black lines in between those layers of graphite. So if you look at the layers of graphite, there's no black lines in between them. That means there's no strong covalent bond between them. There's only weak intermolecular forces, and the layers can slide. So what I would say here is each carbon atom on diamond has 4 bonds. Each carbon atom on graphite has 3 bonds. Graphite has weak intermolecular forces between the layers, so the layers can slide, and that will get me my 4 marks. Graphite has layers which can slide because there's weak intermolecular forces. First 2 marks. Diamond, each carbon atom is bonded to 4 others. The layers can't slide. Okay. Yeah. Right. Use your knowledge and understanding of the structure of graphite to explain why graphite can be used in pencils. We've just gone through this. This is asking you, why does it write off on paper? Why do the layers of graphite slide? Graphite's a great lubricant and it's great in pencils. It's because there's weak intermolecular forces between the layers and the layers can slide. So that's going to get me my marks. Why is graphite a good electrical conductor? So graphite is one of the only non-metal substances that conducts electricity, and it conducts electricity as a solid. So it's either got free electrons or free ions. It's got free electrons. It's like metal. It's got free electrons, and they carry charge through the structure. Here's the answers. Graphite is made of layers, carbon atoms, weak forces of attraction between the layers. Layers can slide. Why is it an electrical conductor? There are free electrons. Because there are free electrons which are free to move, or electrons which are free to move. In fact, you're just going to get the marks for saying free electrons. But I also always add so the charge can be carried through the structure. Some of these questions I'm using are from older exams, and they weren't as specific. The GCSEs have never been so detailed as they are today. Out of the 20 years or so that the GCSEs, or longer than that, 25 years, more than that, however long GCSEs have been going. GCSEs have been going about 30 years, haven't they? They've been going since like 1991 or 92. So GCSEs, since the start of the GCSEs, these are the hardest science exams in terms of the technical language that they've ever been. There's never been as difficult science exams that want as technical language. Now, I'm not saying oh, the kids have got it tougher nowadays, because the grade boundaries have come right down for your exams. So nowadays, to get a level 9 in most GCSE exams, you only need 70% to score the highest grade that can be awarded. You normally 70% is like a guaranteed level 9. So a 50% will almost guarantee you a level 7 every year that the GCSE in the last 5 years of this course. However, the content has got harder, so it's kind of justified that we got the lower grade boundaries. All right, guys, that's it. That was on structure and bonding, just going through some questions to help you. Good luck. Leave a comment. If you've got any questions about chemistry, you can put them in a comment on any of my videos and ask any questions, and I'll get back to you with a reply.